Working of a biological neuron. A biological neuron is the basic unit of any brain, either it's human brain or any other animal brain. And the artificial neuron is imitation of the working of a biological neuron. So it is important to understand the working of a biological neuron. So a biological neuron looks like this. It has three main components. This is called as cell body, right? And these are called as dendrites. These lines are called as dendrites. And this is long tube like structure is called as axon. So let us see the working of these three main components of the biological neuron. So this neuron receives input through these dendrites. The input comes to the neuron through these dendrites, right? The sources of input may be other neurons. That means this neuron receives input from other neurons, or it may receive input from the sensory receptors or sensory organs like ear, nose, tongue, or skin or eyes, right? So input comes from those various resources. Let us call this input, let's say this is x1 coming from some sensory organ or some other neuron. Let's say this is x2, this is x3, x4, so on and so forth. Now not all the inputs are of same importance, right? So some inputs are more important, some inputs are less important. So depending on the importance of the inputs are connected via what is called as weights. So we put weight on the dendrites, like let's say this x1 is connected with weight w1, right? x2 is connected with weight w2, so on and so forth. So more the importance of the input, more is the weight, or thicker is this dendrite. This dendrite becomes thicker and thicker as this input, depending on the importance of this input. After receiving these inputs at the cell body, what this neuron does is it does the weighted sum of these inputs. So that means we multiply this x1 with w1. It is like this: x1 w1 plus x2 w2, input into weight plus other input into that weight plus other input into that weight, so on and so forth. If there are n inputs, we multiply all those inputs with weight and do weighted sum. Now what this cell body, or there is something called as nucleus in this cell body, what it does is, after multiplying and adding all these weights, if that total sum is greater than some threshold, then this neuron produces an output in the form of electrical signal, right? So if the total sum is greater than some threshold, then this neuron produces an output in the form of electrical signal. And if the neuron produces output, we say that the neuron is activated or the neuron is excited. And when the neuron produces output, that output is carried through this axon, right? And that input is taken to the other neuron like this one, right? So these lines here are called as axon terminal. The axon is branched at the end, right? Axon, there are branches of the axon at the end, right? Axon is branched at the end, and through these branches the output is carried to the other neurons, right? So that is how the biological neuron works, and the artificial neuron is exactly the imitation of the working of this biological neuron. So let us see the artificial neuron now. If I represent the biological neuron as in a very simple way, we have this nucleus, or we have the cell body. These are the dendrites, right? The input is coming through this dendrite, right? We are associating weights with these inputs, So then we have the axons here. So these are axons. Of course, there is only one axon, but at the end the axon gets branched. That means there are branches of the axon at the end. That is called as axon terminal. Right. So the output is sent. Same output is sent from here. Same output is sent from here. Same output is sent from here. So here, what is this neuron doing? This neuron is doing some weighted sum, and on top of that, it is getting activated, or it is producing output. So this is the work. This is how we can represent biological neuron in a very simple way. Now artificial neuron, let us represent artificial neuron. Artificial neuron looks exactly similar to this. We have this cell body of the artificial neuron, and then there are the inputs coming here. So x1, x2, x3, x4, this is w1, w2, w3, w4, these are weights, and then here we do sum of these inputs and weights, weighted sum we do, and then this artificial neuron produces output, right? Same output is sent to other neurons. So here in artificial neuron, we perform the sum x1 w1 plus x2 w2 plus x3 w3 plus xn wn. So this sum is represented like this. Now one more thing is there in artificial neuron, that is called as activation function. On this sum we apply what is called as activation function, that is here, and that depending on activation the result of the activation function, the output is sent to the other neurons. So we have the sum here, and on that sum we apply the activation function. There are different kinds of activation function like sigmoid activation function, ReLU, etc. So these are applied on this sum, and the result of that application of the activation function, the output is generated, and that output is sent to the other neurons. Right. So this is how artificial neuron is very similar or approximately similar, though the biological neuron is very complex, but this is this artificial neuron is approximately similar to the biological neuron. So how can we represent a logistic regression by using a neuron model? So logistic regression is a plane separating data points belonging to two classes. Let us say we have these data points which belong to a positive class, and these data points which belongs to negative class. Now logistic regression, this logistic regression is a plane separating these two data points, belonging to two classes. So let's say W is the vector perpendicular to this plane. Now I can write the equation of the logistic regression like this: sigmoid of W transpose X plus B. So this W is a vector which we can write like this: W1, W2 up to Wn, and this X is a single data point with n features: x1, x2 up to xn. Now I can write the same equation like this: sigmoid, this term W transpose X I can write like this. This is basically summing the product of weights and this x's, Wi xi plus b. I just wrote this term like this. So that is how we can write the equation of a logistic regression. Now let us see how can we represent this logistic regression by using a neuron. A neuron has this n inputs: x1 with weight w1, x2 with weight w2, likewise xn with weight wn. So this neuron does the sum here, and on that sum we apply a function which is called as activation function, and this function will produce the output of a neuron. Now if I write the output function which will look like this, O is equal to output, we are applying this function on this sum over I is equal to 1 to n wi xi. So that is the output function of a neuron. Now if we compare the output function of a neuron with logistic regression, which is like this: sigmoid I is equal to 1 to n wi xi plus b. So these two terms, this term and this term, look very similar. In fact, this term is exactly same as this term. In this output function of a neuron, we don't have this b. So in order to get this b, just give input as 1 with weight as b. Now if I write the output of this neuron, it will be exactly similar to this term here. So I just the output of a neuron will look like this: summation over I is equal to 1 to n wi xi plus this b, b into 1 is b. Now the logistic regression and the output of a neuron are exactly same except this f, right? If this f is sigmoid, then this is nothing but the logistic regression. This is nothing but the logistic regression if this f is sigmoid. That is how we can represent the logistic regression by using a neuron model. Now let us see what is a perceptron, right? So this perceptron is a simplest neuron model. Let's say this is the neuron model, again with n inputs. And this is 1 and b. So sum here and f, this output, right? So output is equal to function applied over sum from I is equal to 1 to n xi w transpose wi xi plus b. This is the output of a neuron. So this output, in case of perceptron, this output is either 1 or 0. The output will be 1 when this term here will be greater than 0, right? When this term here is greater than 0, right? That means if w transpose x plus b is greater than 0, when this term is positive, this term I can write like this, right? This term I can write like this. So when this term is greater than 0, the output will be 1. The output will be 0 in other cases. So this perceptron is the simplest neuron model with output either 1 or 0. So we will see how to train this neuron model by using the algorithms like stochastic gradient descent in the next videos or coming videos. Multi-layer perceptron. A human brain or any brain consists of many neurons connected with each other. They are densely connected with each other, and that is a very complex biological structure which is very powerful. So people thought of imitating that complex biological structure by putting artificial neurons or perceptrons together in the layer structure in order to imitate the complex functionality of the natural neural network. So the multi-layer perceptron or artificial neural network looks like this. So these units are, each unit here is a single neuron or perceptron. So these are inputs x1, x2, x3. Of course here we have weights, wi is here, and this is output. So this layer is called as input layer. These two layers are called as hidden layers. This is hidden layer 1, this is hidden layer 2, and this is called as output layer. In a single perceptron, we have only input layer. This was input layer and this was output layer. Okay. So here we have layers of perceptron put together. That's why it is called as multi-layer perceptron. So this multi-layer perceptron imitates the functionality of or it tries to imitate the functionality of the natural neural network. So this is one inspiration for having multi-layer perceptron. Other inspiration is a mathematical inspiration. Let us say we have this complex mathematical function called as 3x square plus 5 cos of root x, right? So in order to construct such a complex mathematical function, we can use multi-layer perceptron, right? So let's say how can we implement this function by using a multi-layer perceptron? So we'll need the perceptrons or neurons performing various tasks or functions. Like one function is multiplication. You see these two terms are in multiplication. Addition, so this term and this term are in addition. Again, this term and this term is in multiplication. We'll need a cos function, we'll need a square root function, right? So such functions we'll need. So let us try to construct such a function, right? Let's say we have this neuron. To this neuron I input x. So this neuron performs a square operation. Let's say square operation. So the output of this neuron will be x square, right? Now I will have a multiplication unit. So this multiplication unit, one input is x square, other input is 3. So this will produce output as 3x square. Now let us say I have this neuron which perform the cosine operation. To this cosine I'll give input as square root. So this will produce the square root of x, and this will produce the cos of square root of x. So that input I'll give to the multiplication unit along with this 5. So this will produce 5 cos of root x, and then I can give this input as another input to another neuron, or the unit called as, let's say, addition. So this will produce the output which will look like this. So such a complex mathematical function can be constructed by using multi-layer perceptron. This is one motivation for having multi-layer perceptron. So when the data is non-linear, right, so that time we can have such functions and we can construct the multi-layer perceptrons structure, or we can use multi-layer perceptron structure for such a complex function. So notations used in the study of deep neural networks. So let's say we have been given a data set with n data points like this. This is data point 1, which is x1, y1, data point 2, x2, y2, data point 3, x3, y3, so on and so forth, data point n, xn, yn. So these are the inputs. X's are inputs, and these y's are the labels or outputs or classes of these inputs. So this y1 is class of x1, or y1 is the output given x1 as the input. y2 is the output when x2 is given as input, or y2 is the class of this data point x2, so on and so forth. So this is a data point, right? Data point 1, data point 2, right? Let's say we have this data point xi comma yi. I pick a data point randomly, ith data point xi comma y. Now the point to note is this xi or ith data point has, let's say, d features, or it is a d-dimensional data point. For example, if this has d features, then I can represent this xi as xi1, xi2, xi3 up to xid, right? So this ith data point or this ith input has d features xi1, xi2, xi3, xid. Now this x1 can be represented like this: x11, x12, x13, likewise x1d. x2 can be represented like x21, x22, x23 and x2d, right? So this is data point, second data point, and this is first feature of this second data point. So here this is second data point, second feature, second data point, third feature, second data point, this is second data point and dth feature. So first data point, first feature, first data point, second feature. So this is ith data point, first feature, ith data point, second feature, ith data point, third feature, so on and so forth. So the notation is, for xi, I am representing xi as xi1, xi2, so on and so forth, xid. So this I represent, it's an ith data point. This one represents, it's the first feature. So if I write this as xij, right? So this means I can write this as xij, ith data point and jth feature, ith data point and jth feature. Okay. So now with this knowledge, let us give ith data point as input. So this is, let's represent this input. Let's say there are 4 features for simplicity. So ith data point, first feature, ith data point, second feature, ith data point, third feature, ith data point, fourth feature. Now these inputs are given to, let's say, 3 neurons. Three neurons we are giving input, right? Let's say we have 2 neurons here and 1 neuron here, right? So this input I am giving here, here and here. This input I am giving here, here and here, right? So this input I am giving here, here and here. This input I am giving here, here and here. So this input, the output of this neuron is given here as well as here. The output of this neuron is given here as well as here. The output of this neuron here is given here as well as here. The output of this neuron is given here and here. And this is the neuron from where we get final output. And let's call this output as yi, because this was ith data point. So that's why this is ith output, right? So output corresponding to ith input. So let's call it as yi hat, because this is not the actual output. Actual data point was xi comma yi, right? So this yi is the output produced by this neural network. Y hat is the output produced by this neural network. This yi hat is exactly equal to yi. That means this data point is producing the output very accurately, right? So now let's represent the function here. This is called as input layer. This layer is called as input layer. This is layer 1. This is layer 2. And this is layer 3 or output layer. This is also the output layer from where we are getting the output. Now this neuron I can represent the function in this neuron like this: f11. This one stands for this is first layer. This is layer 1. Actually this is layer 1. This is first layer first neuron, F12 first layer, second neuron. From the top I am counting neurons, right? This is first layer, third neuron. This is second layer, first neuron. This is second layer, second neuron. This is third layer, first neuron, right? So the representation for the function or this unit, neuron unit, is like this: Fij, Fij. This is the layer number, and this is the neuron number from top, neuron number from top. Yeah. So that is how we can represent a function or neuron. Yeah. Now let's see how do we represent output of this neuron. So output of this neuron is represented like this: O. Now this output is O11, exactly similar to this notations here, 1 1, right? Because this is output of this neuron 1 1, right? So this is also output of this neuron 1 1, right? So this is output of neuron 1 2. This is output of neuron 1 2. Now this line is output of neuron 1 3. This line is output of neuron 1 3, right? So this line is output of neuron 2 1. This line is output of neuron 2 2, and this line is output of neuron 3 1 0 3 1, which is similar to yi hat. Okay. Now we have weights here. Every edge has a weight. Every edge has a weight. So weight here can be represented like this: W. Here we write superscript as the layer in which this weight is going. So this weight is going in layer 1. So layer this, that's why I can write this as W superscript 1, and where it is going, from where it is going, from 1 to 1, right? So from 1 to 1, right? So that's why this is W1 1. So this this talks about the layer in which it is going. This talks about the from which neuron or from which input it is going, and this talks about to which neuron it is going, right? So in general, if I write before that, let me complete this. This is W1 1 2. This is input 1. It's going to second neuron in the next layer, right? So similarly, I can write this as W1. It's going to layer 1. In the layer 1, where it is going? It is going to neuron 3. That's why this is 3. And from which input it is going? It is from 1. This is 1, right? 1 3, right? So in general, if I write weights will look like this: W. This is, let's say this is K. It's this weight is going to kth layer, right? And this is I J. From which neuron or from which input to which neuron? From and to. This is from and to, right? So from to, right? So for example, here if I write weight on this weight is going to layer 3. This is layer 3. So W3. Now it is going from first neuron here in this layer to the first neuron here. That's why W3 1 1. First neuron in this layer to the first neuron in this layer. That's why 2 from is 1 and 2 is also 1, right? So WKIJ means weight W is going in kth layer from ith neuron to jth neuron. So these are some notations which will be quite handy when we'll dive deep into the study of this deep neural networks. So now if you observe one more thing here, these edges are going in this direction, right? So these edges are going in this direction. All the edges, these are input edges, right? So there is no edge which is going in the backward direction. All the edges are going in the forward direction, right? The another thing to note is, or another point to note is, this input is connected to all possible neurons. This input is also connected to all possible neurons. So similarly, this output is connected to all possible neurons in the next layer. This output is also connected to the all possible neurons in the next layer. So when we have such full connections, all connections, such network is called as fully connected neural network. Fully connected neural network. So these two layers are called as hidden layers because they are in between input and output layer. This is input layer, this layer is input layer, and this layer is output layer. So the layers between input layer and output layer are called as hidden layers. So these are the notations. We'll use the notation for studying the other concepts in the deep neural network course. So training a single neuron model. A single neuron model looks like this. We have only one neuron, and let's say there are inputs coming like this. This is xi1, xi2, xi3, xi4. This is w1, w2, w3 and w4, and this is function f, and this is output, which is, let's say, yi hat. So we have a data point xi comma yi, right? We are feeding this input here. Xi has 4 features, or it is 4-dimensional data point, and we expect out to be very close to this yi. So the actual output produced is yi hat, and the actual output is yi. So if this yi hat is very close to yi, the prediction is very good. So now, how to train this single neuron model? So in order to train this single neuron model, we find the weights, which we find the training the single neuron model means finding the correct weights. So now for this discussion, we will consider a regression problem. So in case of regression, we know yi hat is equal to w transpose xi, right? So this is yi hat. So because in case of linear regression, so this yi hat is simply sum of these weights and inputs. So I can write this as yi hat as summation over sum over I is equal to 1 to n wi xi, or this is j is equal to 1 to n wj xi xij, right? Because this, let's say if this is wj, and if I write this data point as xij, when j is 1, so this becomes w1 x1 xi1. When j is 2, this becomes w2 xi2. That means this is multiplied with this is multiplied with this, and then these all terms are added, right? So this is what it means. So finding so training the single neuron model means finding the weights. Training any neural network means finding the correct weights, right? So for the discussion, we are considering this neuron solving a regression problem, right? So now let us write the loss function for this. So the loss is equal to yi. So if this is, let's say, loss I for ith input, is equal to yi minus yi hat. So this yi is the actual output, and this yi hat is the output produced by our model. So if this yi is yi hat is very different from this yi, we will get a bigger loss or greater loss, right? So we want this difference to be very less, right? So we want to minimize this difference. So total loss is equal to sum over I is equal to 1 to n. There are n data points, so it is li, right? So this is total loss, right? So we want to minimize this total loss, right? Now this yi hat for this linear regression, yi hat is equal to sum over I is equal to 1 to n j is equal to 1 to n wi wj xij, right? Or it is nothing but w transpose xi. Same term I can write like this, because this is vector representation of this term. So now so if I write the loss for linear regression, so li is equal to yi minus w transpose xi, right? So this will be the loss for linear regression. Now if I generalize this loss for any model, for any neuron model, maybe logistic regression, linear regression, or any other model. So the loss will be Li is equal to Yi minus f of W transpose Xi. So this W transpose Xi is the sum, weighted sum here in this neuron model, right? So this sum Wi's multiplied with Xi's. So this sum W transpose Xi. So if this in general this f will be this function will be, or this yi hat will be, this yi hat in general will be f of W transpose Xi, right? For linear regression, this will be this function is identity function in case of linear regression. That means this term will be W transpose Xi. That means output input given to this function will be passed as it is to the output. And for logistic regression, if this f is sigmoid, then it becomes a logistic regression, right? So we have this loss now. Loss. Let me go to a new page. So loss is equal to, in general, yi loss summation over I is equal to 1 to n yi minus f of W transpose Xi. So this is the loss function. This is the loss function. And now for linear regression, this is a squared loss. This is a squared loss in case of linear regression. This is a squared loss, right? So here also this loss is squared loss in case of linear regression, right? So this is a squared loss everywhere. Now let us so after the step one is write the loss function. So now I am writing the steps for training the neuron model. Training the neuron means finding the correct weights. So first step is define the loss function, write the loss function. So this is our loss function, general loss function. The second step is write the optimization problem, right? The optimization problem. So here we want to minimize this loss. Now what can minimize this loss? See, in this equation, this yi and xi are fixed because they are input mapped with output. Only variable is w. Only this w can change. That means we want to find a w which will minimize this, right? So we want to find a w which will minimize. We want to find a w which will minimize this loss, right? Loss, which is nothing but summation over I is equal to 1 to n yi minus f of W transpose Xi square, right? So we want to minimize this loss, right? So such w, let us call it as W star. We want to find a W star which will minimize this loss, right? Now how to solve this optimization problem? So this is the optimization problem. We want to find a w or weight which will minimize the loss. So see, in the training process we said that we will have a square loss. We define that loss and then we posed it as an optimization problem, saying that we want to find a w which will minimize this loss. We want to find all w's which will minimize this loss. Now let us see how to solve this problem. To solve this problem, we will use gradient descent or stochastic gradient descent, right? So stochastic gradient descent or gradient descent, right? So what we do in this gradient descent, we will initialize. First we'll initialize weights. So this will be random initialization. We'll initialize the weights w1, w2 randomly, right? Then we will compute the new w new is equal to w old minus eta. This is called as learning rate, right? So then derivative of this represents derivative of loss with respect to w old, derivative of loss with respect to w old. So new weight is equal to old weight minus eta time derivative of old weight, right? So now let us see how to compute this. If I represent this in this is vector representation. If I represent it in the scalar format, so this wi ith weight is wi new is equal to wi old minus eta times derivative of loss with respect to wi old. Right? So that is how we can compute the derivatives. Now that is how we can compute the new weights. Now the question is how to compute these derivatives. That's the question, how to compute this derivative. So let us see how to compute this derivative. So if once we get this derivative, computing new weights is easy. Now and these weights will be updated till the convergence, right? Till the convergence. So let's see how to compute these weights. So derivatives. So we want to compute dou L by this dou W. Right? So this, now if we see at the neuron model, here we have this W1, W2, W3, Wn. So this is xi1, xi2, xi3, xi4, f, and this is yi hat, right? And then this yi hat will be transmitted into loss. So we want to compute this loss with respect to derivative of this loss with respect to this w, right? So that means we want to compute this, right? So now by using the chain rule, we have dou L by dou W is equal to dou L by dou F and this dou F by dou W1, right? So if I write dou L, let's write it for W1, dou L by dou W1 is equal to dou L by dou F into dou F by dou W1, right? So compute this derivative, then compute this derivative, right? Now what is this dou L by dou F, right? Let's compute dou L by dou F. We know F is equal to so we know L is equal to loss function we have defined here. So this is our loss function, right? Let's write this loss function again, or I can compute the derivative here itself. So dou L by dou W1 is equal to, so let me go here. So dou L by, we want to compute this dou L by dou F. So L is equal to summation over I is equal to 1 to n. So Li yi minus f of W transpose xi whole square. So that is the loss function. We want to differentiate this loss function. We want to differentiate this loss function with respect to this f, right? So if I take dou L by dou F is equal to, in differentiation, this power comes down, so it becomes 2 times. So if I take a loss of ith, let me take the loss of ith data point, right? Ith data point. So dou Li by dou W1, right? Rather than finding the complete loss, I will compute the loss of a single data point. So dou Li by dou W1 so is equal to dou Li by dou F divided by into dou F by dou W1. So dou L by dou F is equal to, so this will be Li, right? So 2 times, in derivative this power comes down, 2 times yi minus f of W transpose xi, right? And now we will differentiate this term also, the dou F by if we take the derivative of this term, right? If we take the derivative of this term, the derivative of this term will be 0, and for this term it will be minus 1, because this is f, right? We are differentiating with respect to f. Differentiation of x with respect to x is equal to 1, or differentiation of f with respect to f will be 1. So this now because of this minus term, we will have this minus term here, right? Okay, so now let's see how to compute this derivative. So this derivative in fact is xi. This derivative in fact is xi, because we have sum here. So what is the differentiation of f? F is nothing but output of sum over I is equal to 1 to n wi xi, right? So xi differentiated with this w, so that is nothing but xi, right? So this derivative is xi, right? So now if we compute this derivative, this is nothing but so dou L by dou Wi, dou Li, dou Li divided by dou W1 is equal to dou, we had this dou Li by dou F into dou F by dou W 1. So this term is equal to minus 2 times Li Yi minus f of W transpose Xi, right, into this is Xi. So this is the derivative of this, right. So similarly we can compute the derivatives of all the weights, and thus we can update the weights. Now I can update the weight W1. I can update the weight W1 using this loss, right. So in case of now we can use SGD or gradient descent. In gradient descent we use all the xi's and yi's to compute the derivative. In case of stochastic gradient descent, we can use one data point to compute the derivatives, right, or I can take the batch of data points to compute the derivative. That is called as batch SGD. Okay, so this was how to train a single neuron model. Training a single neuron model means defining the finding the correct weights, right. So updating the weights, right, so that is nothing but training the single neuron model. So to update the weights, we first need to define the loss function, right. After defining the loss function, find the derivative of this loss function with or write the optimization problem. After writing the optimization problem, use the stochastic gradient descent or gradient descent, in which we compute the derivatives of this loss function with respect to weight, and use the derivative to update the weights W by using this formula. W nu is equal to W old minus eta. So this is learning rate. We'll see later how to define this learning rate. So eta times dou L by dou W old. Okay. So training a multi-layer perceptron or multi-layered neural network. So we have many layers here, that's why this is called a multi-layer neural network. So we have input layer, we have a layer 1, layer 2, and this is output layer. So this is how a multi-layer perceptron looks with 2 layers. We may have more than 2 layers or multiple layers. So let us now understand the notations which we already discussed. So we have data set here in the form of xi's and yi. That means we will have x1 comma y1, where x1 is the input, y1 is the output or class label for this input. x2 comma y2, x2 is the input and y2 is the class label or class of this input. So likewise we will have a data set of size xn comma yn, right. So now here this x is input, but that input may have many features, or it may be a multi-dimensional input. So that's why I can write this as x1 as x11, x12, x13, so on and so forth, x1n. So this x input or x1 input has, let's say, n features or n dimensions. So that's why I am writing this as x11 means first feature of input 1, x12 means second feature of input 1, x13 means third feature of input 1, likewise x1n means nth feature of input 1. So that's why it makes sense to write this or let's say if I have this xi, if this is xi, this becomes xi1, xi2, xi3 and xin. So that is how I can represent this input xi, which has n dimensions, right. So that's what we are doing here. We are giving this x as input here, xi as input with 4 dimensions or 4 features. Here every input has 4 features. That's what we are considering here. Okay, so now let's talk about weights. So this weight representation is wi or wkij. That means this weight is going in kth layer from ith neuron in the previous layer to the jth neuron in the next layer. For example, if I talk about this W211 means this weight W2 is going to layer number 2 from first neuron in the previous layer, that is this layer, to the first neuron in the next layer, that is this layer. Right? Okay, so now similarly here this W111 means this is the weight going in layer 1 from first input or first feature here to the first neuron here, right? So now let's talk about these functions or activation functions which are there in these neurons. So F11, or if I write Fij, says that this function, activation function, is in the neuron in the ith layer neuron and the jth neuron from the top. That means this neuron is in the ith layer and its number is j from top. For example, if I say F11 means this neuron is in the first layer and it is the first neuron from top, right? So numbering is like this is layer number, and this j says what is its number from top, what is the neuron number from top, right? Okay, now this O11 says, or Oj says, this is the output. O says output of neuron in ith layer and its number is j from top. So this Oj is similar, or this output number will be similar to this function, activation function here. Okay, so now this is y hat says this is the predicted output for this input. If I was giving xi as input, for that xi the class label or output was yi, but the predicted output, that means the output generated by our neural network, is yi hat. We are calling it as yi hat. And this L says what is the loss, that means how different is this predicted output from the actual output, how different is this predicted output from the actual output, that is called as loss. Okay, with these notations let us start how to train this multi-layer perceptron. So training a multi-layer perceptron means, or training a single neuron model means finding the weights, finding these weights, finding, for simplicity I have written only one weight here. We will have 4 into 3, 12 weights here, right? So here it will be W1 1 2, this weight will be W1 1 2, that means this W1 1 2, that means this weight is going in layer 1 and it is coming from this first feature and going to the second neuron here, right? Similarly here, if I write this weight will be W2 because it is going in layer 2 and it is coming from neuron 3. It is coming from, this is neuron 3 and it is going into neuron 2. So W2 3 2. So training a multi-layer perceptron means finding all of these weights, so that we can have as less loss as possible. That means we want these predicted output to be very close or exactly equal to the actual output. Okay, so now how to train, right? So we will use what is called as gradient descent or stochastic gradient descent, SGD, right? Now what do we do in this SGD? We first initialize the weights randomly. So these weights will be initialized randomly. That is the first step. Next, after initializing the weight, define the loss function. So the loss function here is loss is equal to, if I write loss for a single input, I will call it as Li is equal to yi minus yi hat square. It is a squared loss we are considering for this discussion, plus some regularizer, right? So this regularizer will be used, this regularizer will be on the weights, right? So this is the loss for this single input. Now loss for all the inputs, it's sum of the individual losses. This is the individual loss, right? So loss of all the inputs will be, or let me call this loss as L is equal to sum over I is equal to 1 to n. If there are n inputs, this will be sum from 1 to n yi minus yi hat whole square plus regularizer. So this is the total loss. Now what we want to optimize this loss. We want to optimize this loss means we want to reduce this loss, reducing the loss. So how to reduce this loss? For reducing this loss, you see this loss is in this loss we have y and yi hat, right? Now in the data set we have data in the format xi comma yi. So if we look at this neural network, we have x's and x input, we are giving x's as input and we are getting y as output, right? And we have this w. There are so what is unknown here? Unknown is only w's, I mean, or the variables. The variables are only w's. So we cannot change the input and the output. We cannot change this x's and y's, but we can change this weights so that we can have this minimized loss, right? So that's what we want to do. We want to minimize this loss, right? So how to minimize this loss? By using SGD. So SGD says initialize the weights randomly, right? After initializing the weights randomly and defining the loss function, the third step is calculate a new w. W new is equal to w old minus eta times derivative of loss with respect to derivative of w old, right? By using this formula, we will compute the new w's, new weights, right? Now till what time we will compute this new w's? Till the time of convergence. Convergence means the new weights are very close to old weights. That means there is a very less updation in the weights, right? Till that time we will update the weights, right? Now the important point here is how will I compute this, right? The crucial or crux here is to compute these derivatives of loss with respect to old. So we have to compute, derivative of loss with respect to w1, or if I go here, we have to update each of these weights. We have to update all of these weights. So here we have 12 weights, here we have 9 weights, and here we have 2 weights. So we have to update all of these weights. That means if I want to update this w3, this weight, so I'll have to say w3 11 new is equal to w3 11 old minus eta times derivative of loss with respect to w3 w3 11 old, right? So that derivative we have to compute, right? Similarly, if I want to update this weight, I will have to compute use the same formula, and that time I'll have to compute the derivative of loss with respect to this weight. So I'll need to compute the derivatives of loss with respect to all weights, because I'll have to update all weights. So now as I said, the crux or important thing is how to compute this derivative. This is eta is called as learning rate. We'll learn or discuss later how to compute or how to have this learning rate, right? So the crux of the discussion here is to compute these derivatives. So let's see here how to compute these derivatives graphically. So I want to compute these derivatives. Let me have some space here. Okay, so let us first compute the derivatives in this layer, right? So first let us compute a derivative of this W311. So derivative of loss with respect to derivative of with respect to W311, right? So I want to compute this derivative of loss with respect to this. That means I want to update this weight. That's why I'm computing this derivative, right? So is equal to, right, is equal to, so derivative of loss with respect to this, I want to compute this. I want to compute, let me use this color here. I want to compute this derivative, right? So I will use the chain rule, which is the crux of calculating all these derivatives, right? So I'll compute derivative. In order to compute this derivative, I'll compute this derivative, right, and then this derivative. So derivative of loss with respect to W3 is equal to derivative of loss with respect to O31, derivative of O31, right, and then this derivative of this O31 with respect to W311 into derivative of O31 with respect to derivative of W311, right? So this is called a chain rule, right? So we have this term has to be same as this term, right? And then this is equal to dou L, it is called as dou L by dou W311, right? That is how I can compute the derivative of loss with respect to W311. Similarly, I can compute the derivative of this, right? So let me do it quickly. So derivative of loss with respect to W321 is equal to derivative of loss with respect to O31 now, with respect to O31, and then this derivative of O31 with respect to this weight, derivative of O31 with respect to derivative of W321. So that is how I can compute the derivatives in this layer. Now let us see how to compute the derivatives in the second in this layer, right? So let me again have some space here. Okay, so I want to compute derivative of loss with respect to W211. Now I want to compute this derivative. Now derivative of loss is derivative of loss with respect to this, derivative of loss with respect to W211. I want to update this weight. That's why I want to update this weight. That's why I want to compute this derivative is equal to, in order to compute this derivative, I will compute derivative of loss with respect to O31, right? And O31 is computed with respect to O21, right? And O21 then will be computed with respect to W211. So right, this path I will be following this and this, right? So is equal to derivative of loss with respect to O31, right? Because this O31 is being transmitted here, right? So derivative of loss with respect to O31, and then this derivative of O31 with respect to O21 into derivative of O31 with respect to derivative of O21, and then finally this O21 with respect to W211, derivative of O21 with respect to derivative of W211. So that is how I can compute this derivative. So again, it's a chain rule. So this is the same as this is same as this, and finally we have this term here and here, right? So similarly, all other weights can be updated by computing their respective derivatives, right? Now let us see how to compute the derivatives in this layer, right? Okay, so let me again have some space here. So this case, before computing these derivatives, let us discuss a case where I have, let's say, this x is going in this function f of x, and this x is again going in this function h of x or g of x, let me say, and then these are coming here in h of x, and then this h of x is going into k of x, let's say k of x, right? So if I discuss about this case, how to compute derivative of this k with respect to this x. So I want to compute dk by dx, right? Dk by dx, or let me take it as y, you know, I want to have this as y. So what I want to compute is dy or dou y by dou x. So that is equal to, right? So this h output is going in y, so I can write this as dy by dh, right? Let me not write this x, right? So dy by dh and dh by dx. Derivative of what I'm doing is this with respect to this, and then this with respect to this. Let me not worry about this for now. So this will be dh by dx, right? So dy by dh and dh by dx. Now how to compute this dh by dx? You see this dh by dx, so we have two paths which are coming to this. This is the first path coming from x to h, and this is the second path coming here, and both are parallel paths, right? So when we have parallel paths, I take the derivative of this path plus the derivative of this path. So that means this dh by dx, if I write dh by dx is equal to this with respect to this is equal to dh by df into df by dx, this path, plus dh by dg into dg by dx. So I'll be writing here. So this is equal to this path derivative plus this path derivative, right? So dh by df or dou h by dou f, because they are partial derivative, dou h by dou f into dou f by dou x, plus this path derivative dou h by dou g into dou g by dou x. So that is how I compute derivative of this with respect to this. We have these two parallel paths, so I have to take derivative of this path plus derivative of this path. Again, chain rule will be applied here and here as well. So that is how I will get this derivative, and I'll substitute this here. So then I'll get the derivative of this dy by dx. So the same structure we have here, you know, this we have this. I want to compute this, right? This derivative. So we have this path, right, and this is one more path which are coming here, and then we have this output going into L. So this h is similar to O31, this y is similar to this loss, right? And then we have this path which is similar to this path, and this path is similar to this path, and this is x here, right? Okay, so let's use this knowledge to compute the derivative of this W111. So W1, let me see whether I'll be able to write here or not. Dou L by dou W111. That's what I want to compute. Derivative of loss with respect to this is equal to derivative of loss with respect to O31. It is like derivative of y with respect to h, right? So derivative of loss with respect to dou O31 into derivative of O31 with respect to this W111. So derivative of O31 with respect to W111, right? Now I have to compute this. So let me now make some space here. Just a moment. Okay, so now how to compute this derivative of this with respect to this. As I said, we have two paths, this path plus this path. So I have to compute derivative of O31 with respect to W111. So W111. So this derivative of O31 with respect to W111 is equal to derivative of this path plus derivative of this path derivative plus this path derivative. Again, I will be employing the chain rule here. So derivative of O31 with respect to this O21, right? On this path I have this O21, right? So O31 with respect to O21, and then O21 with respect to O11. Derivative of O21 with respect to O11. This is O11 here, O11, right? So derivative of this O31, O21 with respect to this, and then this finally derivative of this with respect to this, into derivative of O11 with respect to derivative of W11, right? So this is the derivative of this path, right? Now let me take the derivative of this path and add it with this path. So derivative of this path, that is derivative of O31 with respect to O22, derivative of O31 with respect to derivative of O22 into derivative of O22 with respect to O11, O22 with respect to O22 with respect to O11, this with respect to this, and finally this with respect to this, derivative of O11 with respect to W111, right? So now if I substitute this term in here in the bracket, I'll get the derivative of this loss with respect to W111. And once I have this, by using the formula, which formula? This formula, right? This formula, right? I have this term calculated, right? I have calculated all the derivatives, then I can update all the weights. So that is how we can train a multi-layer perceptron. The point here is we need to compute all of these weights, right? So that's it for this video. Memoization. So what is memoization? So let us understand this from the perspective of design and analysis of algorithms. So in computer science, there is a subject called as design and analysis of algorithms. In that subject, we study different algorithm design strategies or algorithm analysis strategies. So there is one algorithm design strategy or paradigm called as dynamic programming. This extensively uses this memoization technique. So let us understand this memoization technique from by taking an example. So here is an example of Fibonacci series. Fibonacci series is a series of numbers which looks like this. The nth number here is equal to sum of previous two numbers. For example, this number is sum of these two numbers. This number is sum of these two numbers. That is how this series is generated. This series is called as Fibonacci series. So here is a recursive function, C function, to generate this nth Fibonacci number in this series. So this is a recursive function. Here I have a recursive call to the same function. Here I have a call to the same function. Right? Now if I call this function for computing 10th Fibonacci number, this is a function call. When I have this call, this complete code will be executed, right? So when I have this call is generating two more calls, because here n is equal to 10. I am passing 10 to this function, so n is equal to 10. N is neither 0 nor 1. So I'll be generating two calls from this function. The first call will be Fibonacci of 9, and the second call will be Fibonacci of 8. So this is a function call again. For this call, I'll have to execute this complete code. For this call also, I'll have to execute this complete code. So that is how the calls will be generated. And if you look at this tree, at the bottom of this tree or at the leaves of this tree, you will have only calls like fib of 0, fib of 1, fib of 0, fib of 1, etc. Right? Only fib 0 and fib 1. Okay, the point to note here is, if you look at the calls, there are many redundant calls. For example, you are generating fib of 8 here as well as here, right? So you are generating fib of 7 here, 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 again fib of 6 here, 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 right, here, in many places. And at the bottom or at the leaves, you see you have number of or many redundant calls, fib of 0, fib of 1, fib of 0, fib of. Now see, this call is a computation. This call is nothing but executing this function and all the function below this. For example, if I'm executing this call, means I'm executing this function once, as well as I am executing this code for all the calls below this fib8, right? So that means this redundant computation is very expensive, right? So but you see, these are redundant calls. You are doing it here and here also, right? So this memoization talks about, right, memoization talks about cutting this redundant calls, right? So when we come across some call or some computation for first time, so we'll do it. For example, I'm executing this fib of 8 for first time, so I'll execute it, and after executing this, I'll store the result of the computation or result of this fib80 call, whatever may be the result. For example, if 8th Fibonacci number, I really don't have answer here, this is 0 1 2 3 4 5 6. A 7th Fibonacci number will be sum of these two, that is 21, and 8th Fibonacci number will be sum of these two, that is 34, right? So answer of this will be 34. Once I get this answer, I'll store it, right? And later, when I come across the same call again, I will not do this computation again, but I'll use the result which already got from the previous computation, right? So that technique is called as storing and reusing, and that is the crux of memoization. Memoization says, if you come across a computation for first time, do it, store the result, and later if you come across the same call or same computation again, use the result from previous computation. So now imagine if I compute fib 8 here and store the result, and now if I am coming across fib 8 again here, right, and now here, rather than doing this see, in order to do this computation, I will have to do this computation, I'll have to do this call, execute this call, then only I'll get the answer to this call, right? So when I come here, when I'm coming for fib of 8 for second time, I can use the result which I already got, right? Thus I can cut this entire computation, right, and save enormous time, right? That is the main idea or crux of memoization, right? Now that is compute once and reuse it, store and reuse. Now same function I can write by using the principle of memoization, which we use in dynamic programming. I can write the same function like this, right? Here we are using this array for storing the numbers. We are initializing these arrays. 0th Fibonacci number is 1, first Fibonacci number is also 1, that's why initialization is done to 1, and then from here onwards just run this loop, right? And for computing any number, right, just add previous two numbers, right? The result of previous two number you already stored, computed and already stored here, right? So that is how we can use memoization, right? So now in our deep neural network, or in training of a multi-layer perceptron, which we already saw in the previous video. So this is a multi-layer perceptron, right? And when you are training this, you are calculating the weights, you are updating the weights. That is the meaning of training of a multi-layer perceptron. Now when you want to update any weight, you will need to compute the derivative of this loss function with respect to that weight. For example, if you want to update this weight, you need the derivative of this weight. Why? Because the formula for new w is equal to old w minus eta time derivative of loss with respect to that weight. So now in order to compute the derivative of loss with respect to this, we use chain rule. Derivative of loss with respect to O31 and derivative of O31 with respect to this, right? So that is the chain rule I wrote here. Similarly, the formula for computing this derivative of loss with respect to this I wrote here. So again, this formula is computing the derivative of loss with respect to this weight. Because I want to update this weight, I'll need this derivative at the time of updating this weight. Similarly, this derivative for updating this weight, and this derivative for updating this weight. Now this is relatively a small network, neural network. In practice, you have very deep or very large neural networks where you have a lot of weights, and that time you will need to compute many derivatives, and computing derivative is not an easy task. It's not a trivial task, right? But can I reduce this computation? Can I make it more efficient, right? If you look at these derivatives, I am computing derivative of loss with respect to O31 here, as well as here, right? As well as here, here, and here, right? You see, in only these 5 derivatives, right? I am doing this derivative computation repeatedly, right? This is redundancy. I can, if rather than computing, see, I am computing here as well as here as well as here, right? That means I am doing the same thing again and again. I can cut that time. So how can I cut that time? Again, once when I'm computing this for first time, I'll do the complete computation, right, and store the result. So I can store the result of this in here. Let's say in this neuron, let's say I can have a memory cell, and I can store this dou L by dou O31, right? So when you compute for the first time, do it and store the result, and later when you are coming when you want the same answer, use the previous result, right? So here, rather than doing this computation again, I can use the result from here. Here also I can use the result from here, so on and so forth. So we can compute the derivatives and store those and use those as and when required. So this is the crux of memoization, and that is how memoization is very useful in reducing the computation or making the computation very efficient.
So backpropagation algorithm. So let's say this is our neural network. It's a multi-layer perceptron where we have input layer. There are these two hidden layers, layer 1 and layer 2, and this is output layer. So we have this data set in the form xi comma yi. So this xi has 3 features in our case, xi1, xi2 and xi3. So there are n data points, x1, x2 up to xn, and each data point has 3 features, x11, x12, x13. So this data point also has 3 features, x21, x22 and x23. So what we are doing is we are giving one data point, this x1, that means these 3 features. One data point means these 3 features of that particular data point as input at a time. At one time we are giving this one data point as input to this neural network. So let's say we are giving this ith data point as input. So 3 features of this ith data point are xi1, xi2 and xi3. So what happens here? So these inputs are sent in the forward direction. So this first feature gets multiplied with this weight W111 and comes here in this neuron. The second feature gets multiplied with this weight on this edge, W121 weight. So this multiplied with this and it comes here. So this feature gets multiplied with this weight and it comes here. And what happens here in this neuron? In this neuron, the sum of these multiplications is carried out. So we have a sum here. If I write a sum symbol here, so this is nothing but sum of these multiplications. So I have xi1 w111 plus this is xi2, this is xi2 into w121 plus I have xi3 into w131. So these multiplications are summed in this neuron, and on that sum we apply this function called as activation function. So the function here is f11, right? And the result of applying this activation function on this sum is nothing but this output. So O11, if I write O11 is equal to applying this function on this sum and that is nothing but output of this neuron. And the same thing happens here. So this input gets multiplied with this weight and comes here in this neuron. So this input gets multiplied with the weight on this edge and comes here. And this input gets multiplied with the weight on this edge and comes here, and this on this sum again we apply this F12 and the result of that is F21 again. So this F11 gets multiplied with this W211 and comes here in this neuron. So we have here O11 into W211. So this O11 gets multiplied with this W211 plus this O12 gets multiplied with this weight here. Weight here is, the weight is W2, it's going in the layer 2, W2, and from neuron 2 to neuron 1. So W2 to 1 plus I have this output here. This output is nothing but O13, and this weight is nothing but W. This weight is going in layer 2, W2. It's coming from neuron 3 and going to neuron 1. So O13 into W231, and on that sum we apply this function F21 and we get the output O21, right? O21 is F21 of this sorry. So that's how we get the outputs of these neurons, and these outputs propagate in the forward direction, and finally we get the output of this output layer neuron. That output is called as O31, or it is also called as yi hat, and this yi hat is the predicted output for this input xi, or this is the predicted class label for this input xi, right? The actual class label is yi, the predicted is yi hat. So we compute the loss for this xi. So the loss for this input is here we are considering the squared loss, or it may be any loss, right? But the loss is, the loss means how different is this predicted output from this actual output, right? So we calculate this loss, right? And then we update the weights, right? And how do we update the weights? By using the formula W new is equal to W old minus eta times the derivative of loss, partial derivative of the loss with respect to W old. That means if you want to update the weight W, that means if you want to get new weight, so new weight is equal to old weight minus eta times derivative of loss with respect to old weight. For example, if I want to update this weight W311, so I write here W311 is equal to W311 new W311 we want to get. So W311 old minus eta times derivative of loss with respect to W311 old. Right? So that means whatever weight I want to update, I need to calculate the derivative of loss with respect to that weight, and by using this formula I can update the weights. This eta is the learning rate here. So now how do we update these weights? Of course, while updating these weights and calculating the derivatives, we use chain rule and memoization, which we discussed in the previous videos. Right? So we rely heavily on chain rule and memoization. So chain rule means, in order to compute the derivative of loss with respect to this, I compute the derivative of loss with respect to O31 and derivative of O31 with respect to W311. So that means if I write in short here, derivative of loss with respect to W311 is equal to derivative of loss with respect to O31 and derivative of O31 with respect to W311. So this is chain rule, right? So we rely heavily on chain rule and memoization. Memoization means we compute the derivative once. That means if I compute this derivative, I will remember it. I'll store it in the memory, and later if I require it, I'll use the that means if I coming across again the same derivative later, I will use the result which we already computed. So that is called as memoization, which we discussed in detail in the previous video. Okay, So now how do we update this weight? Now while updating this weight, we update the weights in this layer first, right? And then the weights in this layer, and then the weights in this layer. So we go in the backward direction while updating the weights. That's why this name back propagation. So while updating the weights, we go in the backward direction. That means we update the weights in the last layer first, then this layer, and then finally in the first layer, right? So that's why it is back propagation. It's called as back propagation algorithm. Okay, so if I summarize now, or if I write the back propagation algorithm clearly, it is like this. The first step is initialize weights randomly. First time you will have to initialize the weights randomly. Then what you do, send one data point, let's say xi, as input to the network, to the neural network, of course. Then what happens? Calculate the calculate the weight, the sum at each neuron, and pass that sum to the activation function, and then the activation function, the result of activation function will be the output of that neuron. Calculate the output of each neuron for 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 the given input. And finally we get the predicted output, that is why I had. So we sent one data point xi as input to the neural network, and then we, for that input, we calculated the output of each neuron for the given input, and finally we get the predicted output yi hat. So this is called as feed forward step, feed forward step, because the input is floating through the neural network in the forward direction, right? And then step number 4 is calculate the loss. Calculate the loss. Right? After calculating the loss, we update weights, calculate the loss for that particular data point xi, so that we are calling this loss as li. Right? Li. This loss is only for that particular data point xi. So then update the weights in the backward direction. So after updating the weights in the backward direction, and till how in the backward direction, so how many times we will update these weights till the convergence. Till the convergence means till the point when old weight and new weight are very similar. That means there is no difference in the old weight and new weight. That means there are no more updates, right? The weights are not getting updated. Till that point we'll update the weights. So these are step 2 to 5. Now we did this step for input xi, right? So we'll repeat these steps. We'll repeat these steps for repeat these steps. Repeat steps 2 to 5 for all the data points. That means we'll repeat these steps for all the xn data points. There are xn data points in our data set, x1 to xn. So we'll repeat these steps for all the data points. That means we'll send all the inputs through the neural network. So when the neural network sees all the inputs from x1 to xn, and when we repeat the steps for all these inputs, so this is called as epoch. Epoch. When the neural network sees all the inputs, right? This is called as one epoch. Send x1 and do this, right? Then send x2 do this, send x3 do this, right? So when we send all the data points and repeat these steps for those all data points, this is called as one epoch. So then finally step 6 is repeat these epochs. Repeat epochs. So this is the backpropagation algorithm, right? So if I summarize the backpropagation algorithm one more time, it is initialize weights randomly. The second step is epoch. In epoch, send xi as input, calculate loss, update weights in the backward direction. In the backward direction. Backward direction means starting from last layer to first layer. And then repeat these steps for all data points. So this is one epoch. Now while updating the weights, we need to calculate the derivatives. And calculating this derivative will require chain rule and memoization. Right? So these two are important things for calculating derivatives, and then only we'll be able to update the weights. And step 3 is repeat epochs. Right. So this is the backpropagation algorithm in brief. Okay. Now the important point to note is, the function, the this function, this activation function, these activation functions must be easily differentiable. These activation functions which are there in the neurons, these must be easily differentiable, right? Why? Because we are calculating these derivatives, right? So derivative of O31 with respect to W31. So we are calculating derivatives. Now, though we are calculating derivatives of output, these output are coming from this activation functions only. That means ultimately we are calculating the derivatives of this activation function. So these activation functions must be differentiable. If they are not differentiable, this backpropagation algorithm will not work, because we'll not be able to compute the derivatives. So these activation functions must be easily differentiable. That's the important point, right? So the other thing which I want to discuss is, let's say we said that we will pass one data point xi at a time as input, right? So this algorithm where we are passing one data point at a time as input is called as SGD, stochastic gradient descent, right? Now when I pass few, like let's say I pass x1, x2, x3, or x4, I'm passing a bunch of data points as input, right? So here I passed only one data point at a time. At a time now I'm passing 4 data points, let's say. So what I'm doing is I'm passing a batch of data points as input to the neural network. So that's why this is called as mini batch, SGD. When I'm passing a batch of data points, this is called as mini batch SGD. And when I pass all the data points at a time, all the data points from x1, x2 up to xn, I'm passing these all at a time as input to the neural network. This is called as standard gradient descent algorithm. Right? So I can use either SGD, mini batch SGD, or the standard gradient descent algorithm. Okay, great. So that's it for this video, backpropagation algorithm. So we'll meet in the next video. So activation functions. So what are activation functions? Let's see. Let's say we have this neuron. We have picked some random neuron from any layer, let's say. So these are the inputs coming towards neuron x1, x2, x3, and these are the weights w1, w2, w3. Now what happens here at this neuron or in this neuron, right? In this neuron here, we take the sum of products of weights and inputs. So what I'm saying is, what we do is we have x1, w1, this input gets multiplied with this weight, plus this input gets multiplied with this weight, plus this input gets multiplied with this weight x3, w3, right? So this sum takes place here, right? So if I write this as sum symbol, or if I write this sum as sum over I is equal to 1 to n, if we have n inputs, so xi, wi, this is what happens here, right? Now what we do here, now after this sum, here we have what is called as a function. We apply this function on this sum, right? We have a function here, right? We write it as f, right? So we apply this function f on this sum, and xi, wi. Now if I call this sum, let me call this sum as z. So z, right? So if I write f of z, I'm writing z for this sum, like f of z. Now applying this function on this sum or this z gives us the output of this neuron, O, right? So this function, right? So O is equal to f of z. So this function f, which is there in this neuron, is called as activation function. Activation function. So what are the different activation functions available? So there are quite a few activation functions available which are widely used. So the first activation function which is widely being used today is called as ReLU. ReLU. So ReLU stands for Rectified Linear Unit. Right? So that is, ReLU is being used from I think from 2012, when deep learning became very much popular, and ReLU is one of the reasons why deep learning became very popular. So pre-deep learning, that means pre 2012 or pre in late in 90s and 80s and early 2000, there were two activation functions which were widely used. The first one is called as or if I write A, it's called as sigmoid activation function, and the second one, or B, is called as tanh. So these were the two activation functions which were popularly used before the advent of ReLU. So let us see these functions one by one. So sigmoid activation function, sigmoid is denoted like this. It is denoted by sigma of z. So we are applying this function, right? This function I'm talking about. This function is it can be ReLU, it can be sigmoid, it can be tanh. These are the three popular activation functions. So now ReLU is most popular. So but before ReLU, as I said, sigmoid and tanh were the most popular activation functions. So this f I'm talking about. So if I say this f as sigmoid, so this will become sigmoid of z. Sigma, right? We write like this: sigma of z, right? So sigma of z is equal to, the formula of sigmoid is e power z divided by 1 plus e power z, which is equal to 1 upon 1 plus e power minus z. If I simplify this, I get this, right? And this sigmoid activation function is also, used in logistic regression, right? It's one of the most important part of logistic regression. So now there are many reasons why the sigmoid was being used as an activation function, but one of the most important reason is, if I take the derivative of sigmoid, of z with respect to z, the derivative of sigmoid of z looks like this. It is sigma of z into 1 minus sigma of z. So this is the derivative of course we are not deriving, we are not writing the derivation here, but I directly wrote the derivation. Derivative of sigma. So derivative of sigma, if you observe, is in terms of sigma only on the right hand side of this equation. If you see, I have sigma here and sigma here. There is no other term, right? So what is the advantage of this? You see, in the neural network, in the forward propagation, in every neuron, if we have a sigmoid activation function, we are already computing the sigmoid of z. In every neuron, we are already computing this sigma of z in the forward propagation phase. And while using back propagation algorithm, we have two phases. The first one is forward propagation, in which we pass the input in the forward direction, and that time we apply the activation function in each neuron. That means we compute, if the activation function is sigmoid, we compute sigma of z. Now in the back propagation phase, what we do, we need to compute the derivatives. We need to compute a lot of derivatives of activation function, right? If you remember, we were saying dou w of, or dou L, not dou w, derivative of loss with respect to w is equal to derivative of loss with respect to some output, right? Some output OI, and then derivative of OI with respect to derivative of loss. So this OI is nothing but the derivative of activation function, because this output is coming out from the activation function. If I this OI is nothing but sigma f of, or sigma of some here, right? This sigma, this is sigma, right? So this OI is nothing but coming out of this sigma, right? So ultimately we'll be deriving this sigma, taking the derivative of this sigma. That means in the backward propagation phase, we will need to compute the derivative of sigma. And you see, what is the formula of derivative of sigma? This is the formula, and in the formula I have only sigma, which I already computed. That means in the back propagation phase I need not do any work. I have already computed these sigmas, right? I just need to plug in the values which I already computed, right? So that is one of the important point about this sigmoid activation function. The derivative of sigma is in terms of sigma itself, right? Okay, now if we see the graph, if I show you graph of sigma quickly, the graph of sigma looks like this. Let's say, so if I plot it, if this is 0.2, 0.4, 0.6, 0.8, and 1.0, and if this is, let me plot the graph. The graph literally looks like this. So at 1, the maximum value of sigma, is 1, right? And it is a S-shaped curve. This is sigma. Sorry. So it is S-shaped curve. The minimum value is 0 and the maximum value is 1, right? So the sigmoid function is a tapering function. That means it tapers off after one, right? The value of sigma does not go beyond 1. The maximum value of sigma is 1. The value of sigma varies between 0 and 1. The value of sigma, this is the graph S-shaped curve is for sigma. So if I if I write, so 0 is less than equal to sigma of z, and which is less than equal to 1. So the maximum value of sigma is 1, minimum value is 0. So that's the important point. Now if I plot the derivative of sigma, it will look like this. So this is approximate curve for derivative of sigma. This is derivative of sigma, right? Now if I say this is minus 4 and this is plus 4, for example. Now if I talk about this derivative, it's the shape of this is a bell-shaped curve, right? Bell-shaped curve, and the important point is derivative of sigma is uh, in between 0 and 1, right? So if I write 0 is less than equal to the derivative of sigma with respect to z, and which is less than equal to, not less than equal to, but it's strictly less than 1. The derivative of sigma is strictly less than 1. So the derivative of sigma varies between 0 and 1. So this derivative of sigma is strictly less than 1. The important takeaway from this is the derivative of sigma is less than 1. It's between 0 and 1 and strictly less than 1. So this is the important takeaway. So derivative of sigma. That's why I have drawn this curve. So because we'll need this knowledge when we'll understand a very important problem with this activation function sigmoid and ReLU. That problem is called as vanishing gradient problem. So for that time we'll need this knowledge. The derivative of sigma varies between or is less than 1. It's like 0.3, 0.2, 0.05, like this. The derivative of sigma is like this, right? Okay, so that was sigmoid activation function. Another activation function is called as tan h. So tan h is equal to, if I write tan h is equal to e power z minus e power minus z divided by tan h of z, of course, e power z plus e power minus z. So this is tan h activation function, formula for tan h activation function. And if I take the derivative of tan h with respect to z, it is 1 minus tan h square of z. So again, the important point about tan h is the derivative of tan h is in terms of tan h, right? You see on the RHS you have tan h, right? It's very similar to sigma. The derivative of sigma, a sigmoid function, was in terms of sigmoid itself. So the same case for tan h. That means once you compute tan h in the forward propagation, you need not do any work while you are doing back propagation, or while you are doing updation in the weights. And that time you will compute the derivatives. You need not do any work because derivatives in terms of tan h. Okay, so again, if I plot the graph for tan h, I'll show you quickly. If this is minus 1 here and this is plus 1, so minus 1 here, this is minus 1. So the derivative of tan h is, this tan h looks like this, right? So this is minus 1 and plus 1. This is 0, right? And this curve is a tan h curve. Tan h, right? Now the important point to note is tan h varies between minus 1 less than equal to tan h, which is less than equal to plus 1. So in case of sigma was varying between 0 and plus 1. So tan h varies between -1 and +1, but the curves are exactly same. The shape of the curve is exactly same. This is also a S-shaped curve, right? So, and now if I plot the graph for the derivative of tan h, it will look like this. So this is how the graph for derivative of tan h. This is derivative of tan h with respect to z. This is tan h of z. Okay. And this, of course, this is z here. So here also I forgot. So this is z. So if we look at the shape of this derivative curve, this is also similar to the shape of a sigmoid curve, right? Of course, this is slightly bigger curve than sigmoid. So now if I write the function, if I write the how this derivative is behaving, it is in between it is 0 is less than equal to derivative of tan h, which is less than equal to 1. So derivative of tan h is varying between 0 and 1. So it can be equal to 1 also. In case of sigmoid, the derivative of sigmoid was right, sigma of z with respect to z. It was less than 1, strictly less than 1, but the derivative of tan h is, it can be equal to 1 also, right? But the shape of this derivative of sigmoid, and now if I plot here, if I plot sigmoid on the same graph, the derivative of sigmoid will look like this. This is the derivative of sigmoid, and if I plot sigmoid itself will look like this, right? So these red curves are for sigmoid, but the point to observe is the shapes of these curves are very similar, right? Again, the point to note is the derivative is derivative of sigma tan h is also like 0.4, 0.3, 0.5, 0.05, etc. Right? So, these were the two important activation functions pre deep learning era, pre ReLU, or before the advent of ReLU. So we understood the shapes of sigmoid, derivative of sigmoid, tan h, and derivative of tan h. So the important takeaway from this is the derivatives are greater than 0 and less than 1 for sigmoid, and for tan h the derivative is greater than 0, greater than equal to 0, and less than equal to 1, right? So derivative of sigmoid is greater than equal to 0 but strictly less than 1, and for tan h greater than equal to 0 and less than equal to 1. Okay, these are the two important takeaways, and we'll use this knowledge in the next video to understand what is the problem if these are the derivatives, right? Okay.